Hey, good afternoon. Um, Today is the last day of classes, so um, there won't be any other lectures, obviously, after this, and this means that we won't be able to cover all the material in the slide deck for file systems. So whatever I covered today will come in the exam, in the final exam, and whatever I don't cover, uh, it won't be covered in the exam. Um, for those of you who are interested in knowing more about file systems, I'll post links to previous year's lectures from ECE, ECE 350, which you can follow. It's based on the same slides, so that should be okay. Okay, so if there are no questions, let's get into it. Okay, so we're going to talk about file systems. File system is basically an abstraction layer that the operating system provides for persistent and named data. Now, there are two elements in this, persistent and named. Persistent means that when a user asks operating system to save particular data, the expectation is that this data will be accessible anytime in the future, unless the user asks again for the data to be removed. And the named part of this means that there is this expectation from users to be able to address their data by human readable names. So the goals for file system is basically to provide this naming. We get the names from the users, and then we map them to their data. We need to manage SDD, whatever that is, to have this mapping from the names to the bytes and blocks of data that we have stored. We need to provide some protection. We don't want unauthorized accesses to be allowed. And we also want the data to actually be durable and not be corrupted or deleted as time passes by. Okay, so what is a file? So a file has a name and set of blocks in file system. So the data is bunch of bytes that user has provided for us, and we as an operating system might save some extra data called metadata for each file. And this metadata could have information about the file. For example, who's the owner, what's the size of it, what was the last time that the file was modified, what was the time the file was created, what are the permissions to this file, and so on and so forth. Now, from the user's point of view, each file is durable. It has a data structure that the user knows. For example, a PDF file might have certain structure in it that users know, the users' applications know. A Word document, a Word file could have a different structure. A text file could have a different structure. So these are all up to user applications to interpret the bytes that are stored in each file. But all they want is for their files to be addressable by human readable names and their files being durable. From the system's point of view, we're just working with an array of bytes. That's basically all we care about. although I have to say, in some certain cases, you might want to know the structure of the file. For example, in Linux, if you compile your file and produce an output, you can double click on that file and then it will execute. So, we talked about this, that sometimes the user interface is also considered as part of the operating system. So in that case, the operating system needs to also know something about the format of the file. But again, it goes to this gray area of, does user interface constitute operating system, or is it part of operating system? We're not going to get into that, but generally speaking, from the file system point of view, we're just working with array of bytes. We don't care what data is in them, what's the structure of that data. We don't really care. The unit of data that we work with in file system is called block. These are logical units, and this could be actually more than a single sector, for example, in HDD, or it could be more than the size of a single flash page. So block is the size of the unit of data that file system works with. It's a couple of bytes, but then it will be mapped to a bunch of sectors. It could be mapped to a bunch of flash pages. There are three types of access patterns to data. So you could have sequential access to the bytes in your file. For example, you can say read X bytes from wherever you are in the file. So for example, you can read a line, you open a file, you start reading lines. So this is sequential. So there is a pointer maintained for you where you are in the file, and then every time you say, give me another line from wherever you are. So this is a sequential read. You could also have a random read. For example, you can open a file and then seek to a particular byte in the file and then start reading it. For example, excuse me, for example, let's assume that you have a file for demand paging. So any page that you want to evict from from your main memory, you save it in a file. And then later on, when you want to bring back that saved file, you're going to access that saved page. You're going to access your swap file and then seek to the beginning of the page that you want to bring in and read that page and then bring it back to memory. And then finally, you might have a content-based access, meaning that you might want to say, I think the best example for this is the Mac OS Spotlight search, where you search for certain file names, right? You say, give me files with this name, or search through the file. For example, you grep into a file and search for a certain word and read from there. So in any sort of, query that you do that is content-based to then read files is content-based access to that file. So there are a couple of examples in this slide you can see. So as we discussed, the unit of accessing files, accessing data in file system is block, and a single block is few bytes. We're not talking about how many bytes, but some number of kilobytes, for example. In normally that would be the case. Now, if you only need to read a few bytes from your file, your file system still is going to work with blocks. So you're going to still fetch a complete block and then just read particular bytes in that block. It's very similar to the concept of paging in main memory, where we lump together a bunch of bytes, we read the page, we have the page, and then we offset into that page to find the particular bytes that we're interested. Now in file systems, the unit is basically blocks, but we still could access bytes. So we'll have to find the particular byte that we're interested in. The same with writing. So if you want to write from byte 2 to byte 12, again, from the file system point of view, you're modifying a block. So the entire block is going to be fetched and it's going to be written. Okay. So even if you're using with getC or putC, these are functions that work with a single byte. You're still going to have to deal with a complete block when you're working with file systems. So there was a study from Microsoft and University of Wisconsin. This study lasted 5 years, and they looked into people's file systems, and they were really interested in many things, but then in this slide I'm showing you two main things that they focused on, which is size of the data. So the findings of this study in terms of size of the files are summarized in these two pictures. Let's look at these pictures in more details. So the first one looks at on the x-axis you have the size of the file, and on the y-axis you have the frequency of a file having this size. And different colors in this graph, different lines show you different years. As I said, this is a study for 5 years, so you have 5 different graphs for 2000 until 2004. Now, what you can see is most of your files are small files. So the peak of this graph, so this is kind of like a histogram of file sizes. This basically shows that there were about, let's say, 3,800 files on average with size 2 kilobytes. So a lot of files with this size. And the peak of this graph went up as years passed by. So this actually shows that we have more files in our system as time progresses, and the peak almost hasn't changed, right? So we're kind of having the same peak, although you might say it slightly has changed from here to here, but kind of you have the peak at the same, almost the same location. So the takeaway from this figure is most of our files are small. Most of our files are small files. So if we want to design anything for file system, we better handle small files efficiently, because most of our files are small. Now let's look at the second graph. This one is a little bit more interesting. So this one is basically the previous graph kind of modified by this. So the x-axis is still the size of the file, but y-axis now is not the frequency, it's a weighted frequency, weighted by the size of the file. So For example, if you have, in the previous example, we had 3,800 files, but then each one of them was 2 kilobytes. So we multiply this, and this gives us, what is it, 76, am I correct? Yeah, 76. Yep, kilobyte, which is almost 7.6 megabyte. So all of our files, so if I look at the storage that has been allocated to files of size 2 kilobyte, it would be 7.6 megabyte. So although I have so many of them, in total, this is their total allocation. The total allocation is really low. So you could actually see it here. So it would be somewhere here. This is 7.6 megabyte here. So on the y-axis, I have the capacity that has been allocated to certain files with certain sizes. Now, looking at this graph, it shows us that, for example, in 2000, files with size somewhere here, it's probably, this is kind of like a logarithmic graph. So I would guess that point is kind of like 10 megabyte or so. They occupied most of, they occupied the highest amount of storage in our system. And as time passed by, this kind of like shifted slightly to 2 megabytes. So whatever is here, the peak was here. So this shows us, although we have a lot of small files, like 2 kilobyte, but they're not going to be occupying much of our space. Much of our space is occupied by bigger files, like 2 megabyte, for example, here. The other thing that is interesting in this graph is the creation or the appearance of this second peak, which is interesting. It's happening here, close to 1 gigabyte. So this says that you have a few big files, right? Why do we know that there are a few of them? Because there is 1 gigabyte. So if everybody has at least one file with 1 gigabyte, then 1 gigabyte should be here. So this is how much storage 1 gigabyte, even if you have one file. So it would occupy 1,000 megabyte. But the fact that it's here, this means that not everybody had a single 1 gigabyte file in 2000. So probably, if we look at this, less than, I would say less than, it's about 10%. So 10% of people that participated in this study had a 1 gigabyte file in their system, right? That's why the size has multiplied by this 10% to get close to 100 megabyte rather than 1,000 megabyte. But by the time in 2004, probably 80% or 90% of people had a single file in their system that was 1 gigabyte. So anyhow, so this other peak here is also interesting. Now, what is the takeaway from this graph? The takeaway is our big files, although we don't have many of them, but they occupy a lot of space. Now, we can argue what is big, what is a small. So with the standards of today, you might say 2 megabyte is not big. With the standards of year 2000, it might have been big. I don't exactly know how this graph looks like now. God knows. Maybe we have a bunch of peaks, not just two. But what we can say for sure is we have a lot of big files these days in our systems. Your backup, your movies, your sometimes your soundtracks. These are big files, and although you don't have many of them, they occupy a lot of space. So again, coming back to the file system design, if you want to design a system, you have to know that you have a lot of small files, but most of your space is going to go to your big files. So this is something that you have to consider. And we'll see, actually, I mean, unfortunately, we don't see, because with FATs, it doesn't matter. But with more modern file systems, it does matter, the size of the file and how you store your big files, which again, unfortunately, we're not going to be covering it today. Okay, so again, observation. The first observation is that most of the files are small. Observation second is that large files use up most of our storage space. Now, this is important to know, and this is important to consider when we are designing file system, but we always have to consider that this is like average case. And if you design your system for average case, your system will suck for corner cases. And that's pretty much what happened with systems like Unix file systems. They're very good with small files, but if you have to do anything meaningful with big files, copying them, pasting them, seeking into them, the system would crash because it's not optimized for big files. What is a directory? So let's talk about that. So a directory is basically a list of human readable names that are mapped, human readable names that each one of them is mapped to a file or a directory. Now, the structure of a directory is usually recursive and hierarchical. So a single directory could contain files, or it could contain folders, and a folder would again be a directory of itself, again having files or directories. So it's a recursive definition when it comes to directories. So you usually get something like this hierarchy of your files. So a single file then could have directories and directories and directories internally. In Unix systems, there is a root directory that usually we show with this character. You should be familiar if you're using Linux or any Unix systems. Even I think in Mac, the root directory is named by this symbol. And then you have a path. So a path, you have two types of paths: the absolute path and a relative path. Absolute path shows this human readable names from the root directory to your file, and relative path shows the relative directions from wherever you are right now. So if you are inside a directory and you want to look at a certain file within the hierarchy of this directory, then you don't need to address from the root. You can have a relative address from where you are right now. So here are two examples. So let's say I have this foo text in directory smz, and this directory smz is in directory home, and directory home is in root. So the hierarchy is root, then home, then smz, and then inside smz I have a foo file. So this would be a absolute path. Now let's say I am right now inside my home directory. Now the relative path to this foo file is smz then foo. So this should clarify different kinds of paths that we have in the system. We might have links to our files. A link is basically another name to the same file. That's what a link means. Now there are two types of links. There is a hard link and there is a soft link. Now the difference between these two, hard link and soft link, is when you delete a file, what happens to the name that you created, the second name that you created. With hard link, if you remove the first name, the file doesn't get deleted, just the first name gets deleted. So if file gets deleted only if all the hard links to that file are deleted. So let's say I have this foo file, and then I have two paths, so two hard links to it. So let's say initially I had this path to file, and then I created this path to link. So I don't know, let's assume that initially this was the file, usr lib7 foo. Then let's say I created this hard link to the same file. So from usr lib foo. Now if I delete this first one, then this path gets deleted, but the file doesn't get removed from the system. It would still be accessible through this second name from usr lib foo. Now this is different if you have a soft link. So with soft link, delete this, clean this up. So with soft link, so again, this shows you the hard link. So if you remove this path, the other path still is valid. So your file will survive. Now with soft links, however, if you remove the first name, the actual name, then the file gets deleted. So the soft links then would be pointing to nothing. So they would be the dangling links. So that's the difference between soft and hard links. Okay. Now, when you want to access your directories, you can access them the same way that you access files, because a directory at the end of the day is stored like a file, a single file. So the same way that you can read a file, you can read a directory. I don't know if you guys have done it in Linux, for example. If, for example, you want to open a file in directory home, you want to say vim, for example, home foo.txt, and you forget foo, you do vim home. Then you actually open your home directory in vim, and you can look at it in text format, depending on your file system, because the directory itself is stored as a file. But so you could potentially use the same system calls that you operate with any file, but usually you have separate system calls to modify directories. So a specific system calls to basically create a new directory, to remove a directory, and to link, to create these links that we just saw. So this is just an iteration of what I said in the previous slide. A file can only be deleted if all of its hard references are gone. If there is a single hard reference to a file, then you cannot delete that file. I'm going to move on from the API of modifying files, because we're not going to actually have time talking about it in any depth. Okay. So the next concept that we need to define is a concept of a volume. Now, volume is a set of physical storage that form a single logical storage. Now, this should be a familiar concept for you, talking about physical and logical, but in case this is not clear, when we're talking about physical storage, we're talking about like you go and buy a new HDD. So this is a physical storage. Now you could get a bunch of SSDs or bunch of HDDs and create a volume over all of them. Basically create a storage volume that, let's say, each one of your HDDs has 2 terabyte capacity, and you buy 10 of them, then you can create a volume of 20 terabyte of data. So that becomes a logical storage. Underneath this logical storage is supported by 10 physical storage resources, 10 physical HDDs. Each instance of file system can manage a logical storage. Basically, each file system can support a single volume. Now, there is a term that is used called mounting. When you have a couple of different volumes, so each volume is going to have its own file system. Now, you can mount different volumes to each other. And what that basically does is basically creates a mapping from where the mounting happens to the host file system. So if you mount volume B to volume A, then volume A is your host file system. Now, if the mounting point, let's look at this example actually, that it's easier to explain it through an example. So let's say you have your USB. So your USB is a single physical storage, and let's assume that you have installed, you have formatted your USB, and by formatting it, you have created a file system on your USB. So that's what you have right now, a single USB with a file system. And let's say the root of this file system, again, as before, is identified. And then let's say we have this vacation.mov file in directory movies. Now, your own laptop or your own desktop might have a volume that you have installed a file system on it as well. So you have your file system, let's say Alice's desktop, Alice's laptop is having its own file system, and Bob's desktop has its own file system. Now, if I mount this USB to this folder volume in Alice's laptop, and I mount this USB separately to disk 1 folder in media directory in Bob's case, then I create this linkage between the two file systems. Now, if you issue a path, if you want to access this vacation.movie, you're going to say, I need it. Let's do it in Alice's laptop. You're going to say, I need volume USB 1 movies, then vacation.mov. So let's say you want to read this. Now, all the way to USB 1 is interpretable in file system, in the host file system. So the host file system tracks it until it understands it. And then from where it doesn't understand, from here it has been mounted, it passes the rest of the file to the second file system and lets the second file system to take care of the rest. So that's the meaning of mounting. You basically create these points that map one file system to another on a single address point. Okay, so the roadmap for a file system is we're going to get a file name, and then in our directory data structure, we're going to map this file name to a file number. Then we're going to get this, and next step is to get this file number, look at something that is called index structure, and find the storage blocks. So remember, these blocks are basically the units of data that we're going to deal with in our file system, and what is expected of us from users is they have a bunch of names and they want to get their files. So we're just adding a level of indirections, and that level of indirection is just introducing a notion of file number. So we get the names, we turn them to numbers, and then we have a mapping from numbers to storage blocks. So let's focus first on this data structure in file system, see how we can implement directories. And once that is done, we'll talk about how we can implement index structure. So these are the two things that we're going to implement in file systems. Okay, so let's start with name mapping. So we're going to get a name, and then we're going to find a file number. So what this means is we have to have these mappings from file names to file numbers. So there are these pairs that we need to maintain. Now, how do we maintain them? The easiest way to implement this is to implement it recursively, because the definition of directory was a recursive definition. So in a directory, you have a bunch of directories and a bunch of files. So we can start with the full name and start with the first directory, and then recursively search for the next directory, next directory, next directory, until we reach to the file that we're interested in. So here is an example. Let's say that this is my let's say this is in my SMZ directory. I have two sub directories. I have SE350 directory, I have EC350 directory, and I have a foo.txt. Now, as I mentioned, each directory is a file for itself. So each one of them is going to have its own file number. So directory SE350, let's assume that it's mapped to file name of file number 739. 924 and 158. So let's assume that these are, we'll talk about how we can do this mapping next, but let's assume for now that they're given. Now, here's how we're going to search for a file. So we start with the root file, the root directory, which is a file by itself. We open it. Now, we do our search. So we're going to search for home, right? So we find home here, and then we look at the particular file number for home. Good. So we have found file number for home. Now let's assume that there is a mechanism that I can say I want file number 119 and I can access it. So this comes next. We'll talk about this next. But for now, let's assume we have this. So next thing I have to do in my search is to open file 119. Let's say we do that. So we open file 119. Now this file 119, let's say it has two subdirectories. It has TAA and it has SMZ. Okay, so again, these are subdirectories. Each directory is a file, so each one of them has a file number. We are interested in SMZ because that's what the search is telling us. Because again, we wanted home, SMZ, and then foo.txt. Okay, so next we open this file 110. Again, assume that there is a mechanism to do this. We open it, and it brings us the directory SMZ, and again, it has two subdirectories, SE350, EC350. Each one of them has its own file, and then it also has our file that we're searching. So this last one. So at this point, we found it. So we get the number. Now we can read 158, and we have found the file that we were looking for. So searching can be implemented easily through a recursive call to read our directories and then keep reading until you find the file that you're looking for. Okay, now this example is fine. Now we want to talk about this mapping between file names and file numbers. That's what we want to talk about. Let's also talk about a data structure that we can use to store our the information in our directories. Again, a directory is a single file. One approach to store data in it is to just do a linked list implementation, right? So we're going to store these pairs of file names and file numbers. We can just do it like a linked list. So for those of you who are familiar with Unix kind of systems, the dot is basically a relative name to the current directory that you're at. Two dots is a short name for a parent directory, whoever is before you. And then, so these two come first, and then again, we're doing a linked list. So we have the first pair linking to, pointing to the second pair. Second pair points to the third pair. So in this example, we're looking at this SMZ directory, which is SMZ file. And then this has this SE350 record pair, and SE350 has a link to ECE350. And then we might want to put some space here for other directories that we might create in this directory, and eventually jump to files, right? So we can store directory pairs at the beginning and then file pairs at the end. So this would be a simple implementation of directory, basically how we store data in our directory files. Now this is very simple. It works fine if you don't have many entries in your directory. So if your directory is like this, the example that we just saw, that I have a single folder and in my folder there are 10 files or I don't know, 5 different directories, this works just fine. But obviously searching through this is hard if you have many entries in your directory. So if you have thousands of subdirectories in a single directory, or if you have thousands of files in your directory, then searching through this linked list is a headache, and it's something that we want to avoid. So an alternative implementation or alternative way of storing these pairs in directory is using trees instead of linked lists. And this is in fact a common implementation in Linux, in Microsoft, in many other famous file systems. When they implement a directory file, they don't just put these file number pairs as a linked list. They store them in a tree manner. So here is an example. For example, we are searching for a name, right? So we have a readable name. We want to find a number for this name. Let's say for Fu, I want to find 158 if I'm not mistaken, in the previous example. Now, here is an example of implementing a directory as a tree. So we're going to get the name that we're searching for. So in this example, we're getting this foo.txt. We hash it to get a number because this particular implementation is a B* tree implementation. This works well with numbers. So we hash the name to a number and then we search for this number. For those of you who are familiar with B* tree, this should make sense. For those of you who are not, then just a simple explanation. In B* tree, you at each node, each parent node, you're searching for a number. Now you start with the first number in your list. So you have a bunch of numbers in each node. If the number that you're searching is less than any of these nodes, then you go to the left side of that node. If it is more than that, then you continue your search. So until you find a number that is more than the number that you're searching, then you branch to the left side of that. So in this case, we're searching for 30. The first number in our list is 240, and 30 is less than that, so we branch to the left. Again, this takes us to a child. The number here is 58. 30 is less than that, so we branch again to the left. Now we have 50, 30, 44, and 58. Now we search for 30. We find it here, so we branch. And then eventually we find the pair. Again, I'm not going to spend time introducing B* tree. I believe this is a topic that you talk about in data structure. But the idea here is we have reduced the search time to log n rather than n. So with a linked list, if you want to search for a particular name, you have to potentially search for n different pairs because you have it in a linked list. In a tree, you search for a name, you reduced it with a log factor, so you pay a lot less cost. Now, how do you store this in your file? Well, here is a possible implementation of this. So this is where you store your B-star nodes, right? Let me go back. Each node in my tree has an array of numbers, an array of pointers. And then eventually I have my files at the end, my pairs. So I use these nodes, the top ones, to search and eventually find a particular file here. So when you come to storing this data in your file, one possible implementation is to put first your pairs at the beginning of your file. So you put them all here, and then you construct your B-star tree. So here, each one of these guys is a node. So here are the, if I were to fill it up, so it's like 240 and then a pointer to a child, for example. Whatever number was here, and then pointers to different things here. So what we're doing here is this requires more space, obviously, because with linked list, all we had was the first part, which is all the pairs that we have, file names and file numbers. Now with this tree, I have to have extra space to store my tree. But then this comes with the benefit of speeding up the search, right? So we're paying storage cost, we're storing more data inside our file, but this is good because when we search, then we pay log n instead of paying n. Okay, so we talked about this. We talked about getting a file name and finding a file number. So this, just to summarize, had two pieces. The first one was the search. How do we search? This was recursive. Sorry if I am misspelling recursive. And then the second part is storage or storing data. How do we store data? So we talked about linked list. We talked about tree. So these are the two things that we talked about the first one. Now let's talk about this second part. Now let's assume that I have my file number. How can I find its corresponding blocks? So that's what I'm going to talk very briefly in the remaining 25 minutes of today's lecture. Okay. So this is what we talked about. We're going to introduce this index structure that gets as an input a file number, and as output gives us storage blocks. So what do we need to know about it? So okay, so this index structure is going to know everything about our files. Where are all the blocks for this file that I'm looking for. Now that I have the number, where are all the blocks? Now, there are a lot of optimizations that you can do with this mapping, but you have to pay attention to a few main things. The first thing is there might be some notion of locality that you have to pay attention to when you're mapping your files to these block numbers. Yeah, you want to make sure that you preserve a spatial locality depending on the storage medium, the physical storage that is going to be used. For example, if you know that your storage is a HDD, you probably want to store your file blocks sequentially so that they are mapped to sequential sectors on the HDD. If you have a SDD, then it probably you just assign them sequential virtual page numbers, but then we discussed this. They're going to move around inside the flash, so there is no notion of where they reside physically in the flash disk. So that's not important much, but to the abstraction that we care about, we just give them sequential block numbers for files that are sequential. If you have, for example, a big file, you probably want to allocate sequential blocks to that, because then that speeds up when you want to read it. Now, the other thing that you want to pay attention to is finding free space. So you know that certain blocks are used for certain files and certain blocks are free. So you probably want to find those free blocks easily, and you also want to avoid any certain fragmentation or spreading of a file. So if you have a lot of free blocks here and there, but they're not sequential, and then you want to write a big file, then you might end up using blocks that are not sequential for your file. So maintaining this free space is also important when you're assigning block numbers to your file. And finally, you want this mapping to be reliable. So what happens if you are creating a file and then you're assigning these block numbers to your file, and in the middle of this, you get a power outage? So what happens to this data structure which maps file numbers to data blocks? You want this to be reliable by itself. Now, all of these add a lot of complexity. So designing file systems is not easy. The first part that we discussed, so going back, this first part, which you get a name and then you find a file number, is pretty straightforward, and there are not much complexity there. The second part, however, when you get a file number and then map it to storage blocks, is complicated and complex. And as a result, there are so many different file systems, particularly different on this aspect. Again, I go back, this notion of mapping is used in many different file systems. So different file systems use the same sort of mapping of names to file numbers. But what makes them different is this second part, where they get that file number and then map it to storage blocks. Now we're going to look at the most elementary or straightforward way of doing this mapping, and this would be FAT or FAT file system. This is one of the, this was introduced in 1977, sorry, and was originally used in floppy disks. I don't exactly know if you have seen one or if you know what these are. When I was a kid, these were very commonplace. So FAT was originally designed for these guys, but then it basically didn't stop there, and because of the simplicity of FAT file system, it became very common in many different storage mediums. So even you can use them right now for your flash disks, for USB files, for example. The idea behind FAT, excuse me. So the idea behind FAT is that file number that you want. So when you get your file number from your name, you use that file, the same file number, you index into the FAT array, and that would give you the first block of your file. From there, you just follow the pointers for your from your first block to find the second block, to find the third block. So you have this, there is a single FAT entry per file. So that would be the first block of your file. So if you're looking for file number 31, remember, I got my name, I looked it up in the directory, I found this name is mapped to file number, let's say 31. Now, where do I find the blocks for this? Well, I come to my FAT array, I look at number 31 entry in my FAT array, and that gives me the first block of my file. Then I want to go to the second one. I follow a link to in this FAT array to find my second entry, my second block, and then this probably has a link to the third block for this file. So for this to work, you need a single entry in your FAT table per a storage block. So whatever your storage is, you divide it into blocks. So that's what file system does. File systems work with unit of blocks. Now for each block in my storage, I have an entry in my FAT table. And these entries are linked together based on the files that I have. Now, a few things about this FAT table. Each entry is 32 bits, basically 4 bytes. And there are linked to each other. Now, let's talk about the properties of this. As I discussed, the file number is the index of root of the block in this list. The unused entries in your FAT correspond to free blocks in your storage. So each one of them that are not used correspond to free blocks in your storage. If you want to grow your file, if you want to write to the bottom of your file, all you need to do is to find a empty fat entry. Let's say I find that this entry is empty. It doesn't matter how you find this. You can do a first fit. You can do from where you are to search for another empty entry, and then you just create a link to that block and mark it as used. This way you expand your file. If you want to create a new file, again, you find an empty entry in your fat table, and then whatever entry that you choose, that becomes the file number for your file. So let's say you want to create foo.txt. You go through your fat table, you find that entry 63 is empty, and you choose that for your first block. This gives you the number that you will store as the number for this file. So this file that you just created gets number 63. If you had picked, let's say, entry number 2, then your file number would be number 2. So there's a one-to-one mapping from your file number and the first block of your file in this fat entry, a fat table, sorry. Now, where do we store this fat table? We store this on disk. So it's stored on the disk. And then we can bring it and cache it in memory, like everything else. One of the things that could happen is you can format your USB or your HDD to FAT. So what will happen is you will just empty all the cells. So you don't need to go to disk and do anything. You just make all your fat entries empty. That's all you need to do for formatting. So now you have a clean fat table. Clean fat table means that none of your storage blocks are allocated, which means that you have formatted your storage. So very simple formatting procedure. Yeah, I guess I talked about this quick format. So with quick format, you just empty all your fat tables. You don't do anything else. If you want to do a deep format, you just go also in your storage and you make everything, you wipe your storage as well, clean. But all you need to do, as far as fat file system is concerned, all you need to do is to free all your fat entries, and that gives you a clean file system. Nothing is stored in it. What is the most significant advantage of fat? It's in its simplicity is the biggest and key advantage of this. It's very easy to find a free block. You just search your fat table for a free entry. Very easy to find a free block. It's very easy to append to your file. Again, all you need to do is to find another empty entry in your fat table. It's also very easy to delete your file. So if you want to delete, for example, let's go back here. Let's say you want to free file 31. So you go to the first entry, you mark it as free, then you follow the link, mark it as free, you follow the link, you mark it free, you follow the link, mark it free, and that's it. So you have deleted your file. You don't even need to go to your storage and delete them from there. You just need to free up your fat table. What are the disadvantages of FAT? So this simplicity comes with a cost, and it's usually performance cost and efficiency cost. So the first thing is, if you want to do a random access to a block in your file, you have to start from the beginning, from the start block, and then search through the FAT entries to find the block that you need. Let's say your file has 1,000 blocks and you want to seek into block 990. You don't have any choice. You have to start with the first entry, go to the second entry, third entry. Basically, it's a linked list. You have to search through your entire file to seek to a particular block that you're interested in. So that's the first disadvantage. The second disadvantage is poor locality. The way you're appending to your files is you're just finding a free FAT entry and then linking that to your old file. And you can imagine that, as time passes by and files get appended and deleted and appended and deleted and appended and deleted, you get to this ugly state where, consecutive FAT entries are allocated to different files. So you don't have this locality that you wanted. Again, we discussed how locality would be beneficial. For example, if you have HDD, if you have your files locally assigned to the sequence of FAT entries, that translates to them being mapped to sequence of sectors, would then make the reading of your file faster. But then, because of the way FAT works, you might end up spreading your blocks for the same file all over the place. So very poor locality. Now, again, this is something that is close to my heart. Back in days when we had old systems with FAT file system, every once in a while we would look at the mapping, and we would do a defragmentation. Let me see if I can find the picture of that. FAT. Yeah, this image is very familiar to many of us who worked with FAT system. So this actually shows you all the FAT entries that are used, and as you can see, there are spaces between them. And then once you would do a fragmentation, it would look a lot better. So it would just put everything, it would put all the, it would try to reorder the mappings so that the blocks for the same file are sequential. So if, as time passed by, you have made your files spread over so many different blocks, if you do a defragmentation, it would try to bring all your data blocks together next to each other, and then try to create, to put all the free blocks next to each other, so that next time you want to append and write to your file system, you can write in sequence of blocks that and preserve locality. So that's that. So defragmentation was something very common. And then once you would do a defragmentation, all of a sudden the speed of your system would be amazing. So for a while, because by doing a defragmentation, you would make your data blocks be close to each other, it would take a long time to do a defragmentation. But once it was done, then your boot time, for example, would be amazing for a while, until again you get to this fragmented state and you would need another defragmentation. Okay, what else? The FAT file system did not support hard links for obvious reason, that the file name, there was no metadata stored for each file, so you didn't have any metadata for your files because of the way that you're storing them, obviously, right? The first block of your file would be the first FAT entry that you have allocated to your file. So all you had for metadata was a few bits in your FAT entry, and FAT entry was 32 bits, right? So you basically didn't have much to store any metadata for your file. And as I mentioned, the way you would find your file was through a single entry in your FAT table. So all of that would mean that there was no support for hard links. The most significant downside of FAST was its limited volume and file sizes. Now, why did you have a limited volume? Well, because each FAT entry is 32 bits. Now, some number of these bits were kept for reserved, so you couldn't use those bits. If I'm not mistaken, 4 bits were reserved. So you were left with 28 bits. Now, if you have 28 bits, this means that you could at most have 2 to 28 entries, because that's how many different things you can address, right? And if the size of each block is 4 kilobyte, then the maximum volume you could support is 1 terabyte. Now, the other issue is, what is the maximum size of each file? Now, again, you're maintaining this linked list of blocks, and where do you store the pointer to the next block? Where you keep that inside your FAT entry. Now, how big is your FAT entry? Well, it has only 32 bits. So what is the maximum number of blocks that you can link together? That would be 2 to 32 minus 1. So basically, that's the maximum file size you could have, which was 4 gigabyte. This limits very greatly the usage of FAT file system. First of all, the volume as a whole cannot be more than 1 terabyte. Second, each file cannot be bigger than 4 gigabyte. Okay, so, and it had a really weak reliability and security supports, precisely because there was no way to store any kind of metadata for your files. Okay, unfortunately, I have to stop here. I hit the time. As I mentioned at the beginning of the lecture, I will provide links from the previous lectures, previous years, to the rest of the slides, basically talking about Linux file system and Windows file system. I also talked about reliability of file systems, only 1 year. I will link that as well to the description on YouTube. So with that, this is going to be the end of SC350. I hope you guys learned something, and I hope this course comes handy in your careers, or if you choose to stay in academia, you would consider doing research or studies in computer systems, then operating systems would be a essential thing to know. So I guess I don't have anything else to say. For the exam, try to study your quizzes. What I'm gonna do is I haven't yet designed the exam, so it will be very close to your quizzes. Of course, all of it won't be true falses, but the quiz questions basically covered everything in the lectures. So maybe I turn a true false question to multiple choices. Maybe I take one or two of those scheduling questions, and I give you a table and I ask you to fill the table, or I will ask you to show your math for calculating the average access time to particular cache or something. If you want to be prepared, I suggest going through previous year's exams available on my website. Definitely go through Berkeley exams. If I were you, I would just look at exams from 2018 until now. So the past 5-6 years, would just go through their midterms, their finals, just look at their questions. There's in the archive, you see both the exam and the answers. That should be enough. And if you have any questions, please don't hesitate. Either post on Piazza or send me an email if you want to meet with me. That would be also possible. Okay, so with that, I'm going to end SE350 Winter 2022. It was a pleasure. I wish you all the best in your exams. I may or may not show up at the final exam, but we'll see. Take care, be safe, and bye.